Well, big things have small beginnings. My name is Bernard Siegel. I'm the Executive Director of the Genetics Policy Institute, and I'm the founder and the chair of the World Stem Cell Summit. And thank you all for coming to San Antonio, Texas. Never have we had a community embrace the summit as San Antonio, with a wonderful 40-person host committee, and we've all enjoyed, if we came in yesterday, an incredible experience with a public day at the University of Texas Health Science Center at San Antonio. Dr. Henrich, it was spectacular, and we had a packed house at every session, starting with the kickoff from Rockefeller University's Dr. Elaine Fuchs, on through the day, major media coverage, by the way, introducing the public to the world of stem cells and regenerative medicine. We also had the San Antonio Research Resource Tour, where some of our attendees attended the backstage tour of the Southwest National Primate Center, Research Center at Texas Biomedical Research Institute, the Southwest Research Institute, and at BioBridge Global, and really had their eyes open about just how important and wonderful San Antonio is and how important it is to the regenerative medicine world. This is a very special time for the World Stem Cell Summit and its organizers. And as you see, this is our 10th anniversary event. Our first event actually was in 2005 at Baylor College of Medicine in Houston, Texas. So we returned to the great state of Texas for our 10th anniversary. And it's a very special event, and you will be hearing a lot more from me, of course, because I'm generally the host of the meeting and as your MC. And I will be speaking probably and telling you a little bit about the journey that that it's taken to get to this point and build this robust community that is really changing the world. We have attendees from close to 40 countries coming to this event. I want to thank our friends from Japan that have really sent a huge delegation to this meeting. And we cannot do it without the phenomenal cooperation of co-organizing partners. The Genetics Policy Institute is a small nonprofit, and we cannot do this heavy lift on our own. It requires the support of major academic institutions and research centers that every year join forces with our organization to produce this event. So I'm very, very honored to call up to the podium representatives of some of the important organizations that have stepped forward. And first, I'd like to call up Dr. William Henrich, is the president of the UT Health Center in San Antonio. Never in my memory of working with the summit have I ever gotten a call one afternoon directly from the president of a major research university saying, hello, I'm Bill Henrich, and I really hope you're going to bring the meeting to San Antonio. That's the kind of spirit we have in this city, and I've had a wonderful opportunity to visit the facilities there and meet the scientists, many of whom are going to be on the program. So let me call up my friend, Dr. William Henrich.
Thank you. I have a simple task today, which is to welcome all of you to San Antonio. A sincere, warm welcome. I promise the sun will be out by this afternoon. The birds will be singing, and it will revert to the usual happy weather that we usually have. We have a little cloudy beginning to the day, but I promise Bernie and I promise all of you it will revert back to the usual pattern by this afternoon. Listen, we're just delighted to have you here. As Bernie says, when we had the chance to bring this important meeting to San Antonio, we were delighted to jump at it, and we are delighted to see all of you here. And the program which has been created is exciting, and I hope all of you find it so. As Bernie mentioned, yesterday on the campus of the Health Science Center, we had almost 400 attendees for what was called a public education day. And it's hard to convey in just a moment or two how much excitement was in the room, how much interest was in the room regarding the fields of stem cell biology and regenerative medicine. We had the young and the not so young. We had a range of people from high school all the way through sophisticated, articulated scientists from around the globe who came to the meeting, and the discussions were lively. And it shows the interest in the field that all of you are well familiar with. It was a new event for San Antonio to see, and as Bernie said, we got a lot of press coverage. Now, you might find something interesting about San Antonio that you didn't know, which is that until recently, San Antonio, Texas was known as the #1 tourist destination in Texas for events such as for attractions such as the Alamo and the Riverwalk, which I hope you'll get a chance to see while you're here. But the leading industry in San Antonio now by far is the bioscience industry, and it touches about $31 billion of activity in our city. So it's far eclipsed any of the other activities that are present in San Antonio today. And at the center of this sits the University of Texas Health Science Center. It's a good idea that if you're going to start a city or start an organization, that it's nice to put a university somewhere near the center, because it's made such a huge difference. And with our partners in the military, with Texas Biomedical, the research park and so forth, we have basically built a formidable industry here. And a large part of that is in stem cell biology. So just have a good time here. I hope the meeting meets your expectations. Bernie and the organizing committee have done a wonderful job in assembling this. The choreography has been terrific. And if there's anything that I can do or that we can do to make your stay in San Antonio more pleasant, we want to do that. Welcome to San Antonio. Thank you very much. Thank you, Bernie.
Thank you. As part of the pre-summit activities in organizing the event, I had the opportunity to take a tour of a place called BioBridge Global, and it wasn't something I was that familiar with. BioBridge Global is a blood and tissue center, but it's so much more. It is an amazing facility where they're doing analysis of blood and tissue for a huge portion of the United States. And to see the activity there and the entrepreneurial spirit of this nonprofit institution was quite amazing. And one of the themes that is going to be revealed and is on the program is the blood and tissue banks of the world are going to play a major, important role in the future of medicine. And that's one of the themes that are going to come alive at this meeting. BioBridge Global is hosting 2 special lunch symposiums on Thursday and Friday. And you're going to have some difficult choices to decide on different things to attend. But these are very, very important sessions. And as I was working with the leadership, of course, I came into contact with Dr. Linda Myers, who's their CEO. And Linda, you run a spectacular organization with people like Sean Thompson and so many others that have really embraced the summit. Linda is co-chair of the 40-person San Antonio Host Committee, and I want to invite her up to say some remarks. Thank you.
Thank you. Good morning and welcome to this early session. I just want to give you a little overview of BioBridge Global and tell you why we're here supporting this conference. 40 years of history. Our mission with BioBridge Global and its subsidiaries has been to save and enhance lives worldwide. Over those decades, we have actually enhanced our infrastructure within our not-for-profit organization to holistically support the field of regenerative medicine. So throughout all of our facets of our organization, we really focus on research and in enabling those technologies, along with our long history in the community of collecting and developing a donor base that supports our mission is really what feeds our success. So BioBridge Global actually is made up of several subsidiaries, one of them, GenCure. And do I advance this? Do I advance this? GenCure is really our subsidiary that focuses on regenerative medicine, and it's made up of several components. We have a tissue services center, which collects, processes, and distributes human-based tissue products throughout the region for patient therapy and also to support research. We have an umbilical cord blood bank at our facility that collects, processes, and stores cord bloods. For the public, Texas Cord Blood Bank, patients worldwide have received transplants out of this program, and any product that doesn't qualify to be registered in the public registry is made available for research. We also have a cell therapy division which utilizes apheresis technology for the collection of peripheral stem cells, dendritic cells, and lymphocytes to support clinical trials in our region and further. The other subsidiaries that we have include South Texas Blood and Tissue, which is a large blood bank that collects and distributes products not only in Texas but beyond. They are actually celebrating 40 years of service in our community this year and are known as the transfusion experts here in our region. Qualtex Laboratories is the largest not-for-profit testing lab in the United States. It's an independent testing lab. We have facilities here in San Antonio, Texas, as well as Atlanta, Georgia, and Qualtex is dedicated to public safety by doing an advanced infectious disease testing and also other specialized testing. They test over 8 million samples a year. The other entity that we have is the Blood and Tissue Foundation, and the members of the Blood and Tissue Foundation have raised millions of dollars to support and fuel the research and the work that is going on at BioBridge Global, and they are very important partners for us as we move forward. We are very proud of the fact that we have a unique ability to enable and support regenerative medicine, and that's really why we're here today, supporting and being a co-partner for the 2014 World Stem Cell Conference. So we're very pleased to have you here. Thank you for allowing us to showcase our company, and we would also like to invite you by our booth in the exhibit area. Thank you so much.
In the early days of the summit, we used to organize our meeting with just regional partners. But a few years ago, we found that there was a desire of some of institutions, important institutions from around the world, that became very, very interested in the work that we were doing in trying to advance the field. And they joined forces and have helped us organize these meetings. I want to introduce one of our good friends, and that is Dr. Norio Nakatsuji. Dr. Nakatsuji is at Kyoto University, and he's the former director of the Institute for Integrated Cell Material Sciences, iCeMS. It's one of the giant pillars supporting regenerative medicine at Kyoto University. And of course, as Japan has emerged as a leader, they've got their act together. Their regulatory system, the government support, a plan, it is really a beacon of at least how one leading nation can push this field forward to bring this to humanity and the potential for cures sooner rather than later. Dr. Nakatsuji has been a wonderful partner and his excellent team, and there's a very robust delegation, as I mentioned, from Japan at this meeting. We're honoring tonight at the Stem Cells Awards dinner at the Japanese Society for Regenerative Medicine. with a Global Leadership Award. It's an amazing society, and you'll be hearing more about that later. So let's welcome to the podium Dr. Norio Nakatsuji.
Thank you very much for a very kind introduction, Tony. I think you all agree that we have a very exciting time for the stem cell and regenerative medicine area. A recent survey published in Regenerative Medicine shows there are more than 1,000 clinical trials going on around the world. And naturally, the majority is using hematopoietic stem cells and mesenchymal stem cells. However, there are already six clinical trials using embryonic stem cells. And as you know, recently, the one clinical trials has started in Japan using induced pluripotent stem cells. So I hope, I'm sure soon probably the most powerful and versatile stem cells, it's pluripotent stem cells, shows power in patients. So to go further, we need more involvement of the industry and capital for realization of the regenerative medicine for many patients in sustainable manner. So in that sense, this forum, this summit is leading the world trend, emphasizing that kind of aspect with many capitalists coming. So I'm very honored to be one of the co-chair of this meeting for several years. And particularly this year, I'm very proud that many key persons from Japan are attending this meeting and give talks, such as one core person who actually wrote the recent regulation in Japan. So I hope you enjoy the interaction with together, particularly with Japanese scientists and key persons. And we need not only multi-sector collaboration, but multinational, international collaboration and partnership. And I really hope that with the pushing power of our government, emphasizing on regenerative medicine, there will be many collaboration and industry partnership between the Japanese company and scientists with global scientists and companies. And thank you very much and welcome.
I started the Genetics Policy and started our wonderful collaboration with the Mayo Clinic when we ran our meeting in West Palm Beach, Florida in December. And I always wondered if the weather had anything to do with it, but I don't think so. The Mayo Clinic has been integral to the design of the World Stem Cell Summit program and has robustly supported what we've been doing. It's the largest medical practice in the world, based in Rochester, Minnesota, and in Arizona, and in Jacksonville, Florida. And Dr. Andre Terzic, who heads up their Center for Regenerative Medicine, a true visionary in the field, and a recognized visionary, really assisted and guided the program this year in the tracks that we have. And I think that all of you will appreciate some clarity in the program as far as its design and intent to move this entire field forward. The Mayo Clinic represents the highest ideals of scientists and clinicians working together to advance our field. And we're very honored that Dr. Terzic is again a co-chair of the meeting, and that we and Mayo Clinic is an organizing partner.
Thank you very much for these very kind words, and indeed on behalf of the Mayo Clinic, we would like to welcome you all here today. It's an exciting time. It's an exciting time because on one hand we recognize the unmet needs of the patients nationally but also globally. The pathodemographics are changing very rapidly, and then on the other hand we have such a revolution in terms of technology breakthroughs, and the innovation that is coming is paving the way truly of a transformative moment in medicine. So in this spirit, I think this forum is put together as a vehicle to bring together various aspects and create truly a community of practice that will be sharing best practices, but also moving the field going forward. So on behalf of the Mayo Clinic team here represented by various components, the research component, the practice component, education, we indeed are very, very proud to be part of this effort, especially at the time where regenerative principles are increasingly becoming regenerative practices. Thank you very much.
Thank you, Andre. So I'm going to invite my speakers off the podium. Let's give another round of applause, please. Also supporting the meeting is Baylor College of Medicine in Houston, Texas, and with the wonderful support of the Huffington Foundation and our good friends, Dr. Ralph Dittman, and we're hoping he can make it. He's been in poor health recently, and his wife, of course, Terry Huffington. The Baylor College of Medicine is going to be represented this evening at the awards dinner, where we're going to be recognizing one of the true leaders is Dr. William Brinkley with the Hero Award. He was president of the creation and the initial co-chair of the World Stem Cell Summit, was when I think we were calling it the Stem Cell Policy and Advocacy Summit back in 2005. Also supporting this meeting as a co-organizing partner is the Regenerative Medicine Foundation, wonderful organization founded by Dr. Tony Atala, our first keynote speaker, and more about that in a few minutes. So I'm going to try to give you in a few minutes a lay of the land of the meeting. And of course, I'm sure if I ask for a show of hands, how many people have downloaded the app for the meeting? This is really impressive. This is really impressive. Thank you. So what we're doing, living in modern times as we are, make sure you download the app, because if you're looking around for a program book, you are not going to find it. We have a loose guide. The wonderful newspaper, the San Antonio News Express, provided an insert with our program. Of course, we've reshuffled the room since then, but it gives you a general outline of the meeting, and you put on your reading glasses if you're old, and you can read the print because it's a complex program. But you look at that, and you can also see how the program unfolds into 6 concurrent tracks, and of course, our RegMed Capital Conference. If you need help, go to the desk, where the great team from Synaxis Meetings will point you in the right direction. And also, we have a lot of monitors that can point out. The rooms had to be shuffled for recording purposes and other various meetings, so the only track that's going to stick in the room that was in the program a week ago on your agenda is the RegMed Capital Conference. The World Stem Cell Summit is an experiment, and we've tried many different and new things. It is brought to our population and our global community to bring you innovation, new ideas, and new thinking. So this is the first year we have a dedicated track, a co-located meeting called the RegMed Capital Conference. And if you attend the meetings in this room, you will find some of the leading investors, the new money, the venture capitalist world of the Keiretsu Forum, the largest forum of accredited investors in the United States, in the world actually, 1,100 members, and several of them are in attendance today, but they're carefully looking at the world of regenerative medicine. We have the Targeted Technology Fund, a local but really well-run fund that is making investments in regenerative medicine. as one of the sponsors. And you will hear company presentations, 12-minute presentations about companies, everything from startups to public companies that are in this emerging field. You will also get the wisdom, collected wisdom of investment gurus, investment banks, leading IP attorneys, those that have looking for a big overview of the scientific underpinnings for this field. This is an emerging multi-billion-dollar industry that is going to change the world. Think about the beginnings of the internal combustion engine or the semiconductor business. This is a revolution that's taking place. These meetings that we've been having the last 10 years are the first seeds that are being planted about this. This is going to sweep the future in the next century and impact not only our lives, but the lives of our children, grandchildren, and future generations. And it's all happening now. So how we translate this and get our companies funded to start is a critical unmet need. And when we started this meeting in 2005, we had one little track with some companies on it, some of the pathfinders, Geron, Advanced Cell Technology. Now this meeting embraces the entire gamut of regenerative medicine and advanced therapies. It's not about embryonic stem cells or reprogrammed cells or adult stem cells. It's everything that's moving forward in this field. That's what you have before us. This is a smorgasbord of so much information. The algorithm of planning this conference is so complex. Actually, you need a PhD to do it. It's surprising that I'm standing up here because I don't have a PhD. But anyway, I think you get the message. It's up to you to make the connections. This year, we have a very sophisticated partnering program. It's called Jujama, or Jujama. And Jujama is a very, very good program. You can open up your app and see anyone that is at this meeting. You can make an appointment. You can look at some of the biographical information and make a connection. This meeting is designed for networking. There are some researchers that travel halfway around the world to give a 15-minute presentation on a program, but are here for the networking. So if you in the audience don't make the effort to connect with that speaker, you are missing out at a golden opportunity to advance your interests at this meeting. Whatever there are people that can advance your interests. So don't be shy. At our first long break at 12:30 to 2:30, Genetics Policy Institute is supplying you with a gourmet boxed lunch. If you've pre-registered for it, you pick up your lunch. If you don't have lunch, it doesn't matter. There's plenty of food everywhere around the Riverwalk, and you even get a discount with your badge in some of the places, so look for it. Starbucks downstairs. But you can sit at our Conversations with Experts luncheon. We have 30 expert tables. You pick a topic, pick a speaker. The information is in your app. We'll also have people to guide you to these tables. It's in the exhibit hall next door. Do not miss this opportunity to sit down at a table with an expert for a free-flowing, friendly conversation with other people that are interested in your topics. What are some of the themes that you're going to hear? You're going to find out that we're using stem cells in microgravity. We actually have an astronaut, former astronaut David Wolf, who was at the International Space Station in Mur. He's going to be doing an expert lunch. NASA is here. The Center for Advancement of Science and Space is in the house. They're next door in the exhibit hall. We have sold out our exhibit hall, a robust exhibit hall, a fantastic poster session. And believe me, without our wonderful sponsors, our platinum sponsors, such as Cord Blood Registry, Stemedica, Marianne Liebert Publishers, I think there's another one. It'll come to me, and whoever it is, this is the first of many when I'll forget. But I'll come back to it. The point is all of these sponsors and their support for this meeting have made all the difference in the world, and there are a real diversity of interests. This meeting is different than any others, and the reason this meeting was created 10 years ago, I was invited with some of the leading scientists at the initiation of the International Society for Stem Cell Research. My background was law. They were looking for a legal mouthpiece, in effect. So I took this up as a cause, as a cancer survivor. And at the first meeting of the ISSCR, as a civilian, there was nothing I could understand. I could chat with some of the leading scientists who had invited me to the meeting. I could understand the ethics, and I understood the regulatory aspect, and I was talking to the exhibitors. The patients did not seem to have a forum. This organization, our nonprofit organization, is designed to advance the patients and their needs. And there are outstanding representatives of patient organizations, from major societies to just grassroots folks and individual patients' families in the room. And when a scientist working with cells in a petri dish meets a patient that will one day benefit from the research, it is a magical moment. And it's one of the reasons that we're here. And I want you to embrace this meeting and toss out anything that any other meeting that you've ever attended. Because this meeting is meant to be something that's special and important and will work for you. My team, the Genetics Policy Institute team, is here to serve you. My Associate Director, Alan Fernandez, who many of you know, right arm. This meeting could not have taken place without them. We have a wonderful communications team with Joseph Dawson and Mara Leventhal, administrative team with Jerry Friends, a very small organization, but actually very dedicated to making this experience for you work. I have the pleasure now of introducing one of our leading scientists on the planet in the field who's going to provide some keynote remarks. Of course, that's Dr. Anthony Atala, Director of the Wake Forest Institute for Regenerative Medicine and Chair of the Department of Urology at Wake Forest University. I had bumped into, in the journey over 11 years of working in this field, bumped into Dr. Atala several times at different meetings. I never really understood exactly what his path-finding work was all about. I knew he was a leader of the Armed Forces Institute of Regenerative Medicine as a major researcher and organizer, bringing cutting-edge research for our wounded warriors. I knew that he was working with biofabrication, biomaterials. But until I visited the Wake Forest Institute of Regenerative Medicine in North Carolina, in Winston-Salem, I didn't realize that it was probably the single largest regenerative medicine institute in the world under one roof, with its own tech transfer office, and with a mammoth capacity for research. Now, unlike myself, Dr. Atala is a clean desk man. Somehow he keeps his desk clean and well organized and finds a time to go in once a week and actually perform surgeries, and with heart and compassion that you would not find anywhere else. His biography, his full biography, is in the program app, so I would ask that you take a look at it. But what I wanted to just mention is that one of the things that Dr. Atala did was create a nonprofit organization, a 501c3, as is Genetics Policy Institute, a charitable organization, for public awareness of regenerative medicine, called the Regenerative Medicine Foundation. Over the years, we've observed and cooperated with them, and they have put on a gem of a meeting every year. They have an official journal, Stem Cells Translation from Advantage Media. They have a wonderful program. They've commissioned art to symbolize the field of regenerative medicine. They have moved this field forward in a very positive way. As we met and talked over the months, and they became a co-organizing partner of this summit, we realized so many of the efforts of Regenerative Medicine Foundation, Genetics Policy Institute, were duplicated, that we started discussing, and we have a major announcement today that's going out on the newswire, that the Regenerative Medicine Foundation and Genetics Policy Institute will be merging and to be one force and one largest voice for patient advocacy and the advocacy of this science. And this is going to happen in the first quarter. The announcement has been made even as I'm speaking today. We are so honored to be partnering with the Regenerative Medicine Foundation, and we anticipate that the name of Genetics Policy Institute will be Regenerative Medicine Foundation in the coming year, and Genetics Policy Institute will be the Policy Institute think tank of the group. So I want to introduce my friend and colleague, Dr. Tony Atala, to the podium.
Thank you, Bernie. Bernie, thank you so much. Thank you so much. Appreciate it. Bernie, thank you so much. I'm very excited to be here with you today, and also for the coming partnership, which is going to be really great to have us working together and the foundation members working together. Bill Hinman is here, who's executive director of the foundation, and Ann Murphy's also here from the journal Stem Cells Translational Medicine, Alphamed Press. So I think it's going to be an exciting time for the field as these two organizations come together. And it's great to be with all of you today. What I thought I would do today is, Bernie asked me to come on and speak. This was before we actually started the discussions of the merger. This is quite a while ago. And basically it was to give you a little bit of an overview of regenerative medicine and some of the things that we're doing in this area. So I guess this clicker is not going to work, so we'll go signals then. Next slide. Thank you. So basically, this is actually a painting that hangs at the Conway Library at Harvard Medical School. And it shows the very first time that an organ was transplanted. In the back room, you see Harlow Harrison, who was the chief of urology at the Brigham and Women's, retrieving the organ, which was a kidney. And then you see Joe Mary in the front implanting this organ. And this is an important event in our field, because it really marks the very first time that an organ was ever transplanted, and so many lives that have been saved by this one single event. But we're still dealing with challenges in terms of organ shortage and rejection, which we still must deal with. So basically, this is where this field comes in, and as you know, the field has really grown over the last 2 decades, two and a half decades, with the use of cells alone, or cells and materials alone, or basically both of them together. And we also have a lot of work right now in enabling technologies in the field of small molecules and regeneration. And for the interest of this talk, we will not cover that today. The field really goes back even further in terms of its origins. This is actually a book that was published back in 1938, titled A Culture of Organs. And you can see the two authors here, Alexis Carrel, another Nobel Prize winner, just like Joe Mary. He actually was a vascular surgeon who implanted the very first grafts for blood vessel surgery. We're still using some of those grafts today. And then the co-author, who's Charles Lindbergh. That is the same Charles Lindbergh who actually flew across the Atlantic back in the 1920s. So the field's been around for a long time. So then why so few clinical advances in the last 2.5 decades? Really many challenges that led us to where we are today, where finally we're seeing a lot of these technologies being used in clinical trials. But the first challenge was really the inherent inability to grow and expand cells outside the body. This field got its origin before even mesenchymal stem cells were actually discovered, before human embryonic stem cells were discovered, before cloning came about. The second challenge was biomaterials. How can we actually get these materials in patients? And the third was vascularity. And we'll discuss these briefly. One of the major areas that really got us into this field in the early days was growth factor biology. How could we actually get these cells to grow outside the body? It was thought at the time that the cells had a natural senescence. Most primary human cell types had a natural senescence that could not allow you to basically expand these cells outside the body. So a lot of the studies that we did in the field were in the growth factor biology area. One of our very first funding grants was basically on trying to look at the growth factor biology of urothelial cells, which are the cells that cover the urinary tract. These cells could not be grown or expanded, but by looking at the growth factor biology and recognizing the presence of what we now call committed progenitor cells, we were then able to expand these cells in large quantities. We could take a very small piece of tissue, less than half the size of a postage stamp, and by day 60, we could have enough cells to cover a football field. This is really what led us to some of the advances that we made in those specific organs. But if we fast forward 25 years later, now pretty much every single cell type from humans can be grown and expanded outside the body, pretty much. Not all. Even now, 2014, there's still several cell types that we cannot go to a patient, take a biopsy, and get those cells to grow and expand outside the body. And these are listed in black. So still a lot of discovery that needs to be made in this area. Now, you can take stem cells and drive them to these cell types, but you cannot take the primary cells from the same patient, expand them, and put them back into the same patient from these specific organs. So still some work that needs to be done in this area. The second challenge was biomaterials. How do you actually deliver these cells inside the body? And many advances by many bioengineers all around the world, material scientists, trying to get materials that we could use to implant these cells in the body. And they should have all these characteristics here. And basically, when you're thinking about implanting cells, really the scaffold should really be permissive to the formation of the cells and the tissue that you're trying to form. The third challenge was vascularity. Really, now we have these cells that we want to put into the body, but the fact is that there's a maximum diffusion distance by which cells will survive. Back in 1973, Judah Fogman, the founder of the field of angiogenesis, established this very simple principle that cells could not expand outside, could not survive outside the body or inside the body in volumes larger than 3 millimeters cubed. This was a maximum diffusion distance if you wanted tissue to survive. And so this presented a challenge. We now have enough cells to cover a football field, but we can only implant cells the size of a pencil eraser without survival if they don't have adequate vascularity. So how does nature solve this problem? And nature solves this problem by branching from the lowest forms of life, such as algae, which you may see at the bottom of the ocean floor, to a leaf, to a tree, to the branches of an organ. Vascularity and branching is a solution to nutrient diffusion. And that is why many material scientists started to design these scaffold systems that had a branching pattern that would allow the cells to lay down on these scaffolds, and the branching pattern would be permissive to the neoangiogenesis and neovascularity necessary for these structures. Back at our institute, we ended up looking at other permissive vehicles for vascularity, and we were able to show that really this is the most important factor for success in terms of future tissue formation. If you look on the far left, you see that if we implant muscle cells alone, nothing much happens. If we add endothelial cells, you have a little bit of vascularity. If we add the most potent growth factor, vascular endothelial growth factor, you now have a lot of vascularity. But there's no doubt that the best tissue formation occurred when we had the muscle cells plus the growth factors, plus the endothelial cells, and now you really had a very nice piece of muscle tissue that was formed from these injected cells in the animal model. So really vascularity is key to the formation of these tissues. One of the first tissues that we targeted was the urethra. That's the channel that connects the bladder to the outside of the body. These are some of the very early experiments we did in the early 1990s showing that we could use these scaffolds that we would decellularize. We basically would use very mild detergents to take the cells away of these bladder tissues, and we would then use that scaffold made out of collagen to replace a urethral segment. You can see here a rabbit urethra, a segment was excised from that urethra, a tubular segment. Then the scaffold was tubularized and placed in that defect. And what we found was that, yes, you can use these scaffolds for regeneration without the cells, but only for limited distances. If you needed larger distances, then you really needed the scaffold and the cells together. So about 6 years later, we had our first patient that we wanted to see whether we could really regenerate these tissues in patients using these scaffold techniques. And this was after a lot of basic research, of course, but here's a patient showing you the area of the injury. And you can see that the bottom portion of this organ is still normal. It's only the top portion that is abnormal. So what we did is we basically replaced only the top portion of this tubular structure. And by doing so, we were able to observe this maximum distance of cell migration, which is about 0.5 centimeter from each edge. So basically what's happening here is that the cells from the bottom tissue, which are normal, are walking on that bridge, if you will, and bridging the gap. If that distance is larger than half a centimeter from any edge, then scar will form. So you really want to limit these to small surface areas. And by doing this, we're able to replace the entire top portion of this structure, and this actually led to tissue regeneration. The question here, after you see an X-ray like this, is this really regeneration, or is it really just a stent that's in place? In fact, it is regeneration. What happens is the cells walk on that bridge, and then that scaffold that we put in, that collagen scaffold, is fully degradable. 6 months later, it's gone, and these cells lay down their own scaffold, while the scaffold that you put in goes away, in fact, leading to true regeneration. This is actually an endoscopic view of that patient prior to surgery, showing you the area of the stricture, with a scope being placed right at that region. And on the right, you see the fully regenerated organ by that scaffold. Now, here's a patient who presented to us many years later. And this is a scaffold. This is a patient who had a major injury. He was involved in a motor vehicle accident. And you can see here that the organ is shattered. Basically, there's a large distance between the bottom of the bladder and where the urethra is. And when contrast goes into the bladder, it's just extravasated. So what we ended up doing is we brought the patient in about 4 to 6 weeks prior to their scheduled surgeries. We brought these patients with similar injuries. We took a small piece of their tissue, normal tissue. We expanded the cells. We created the construct. We placed one cell type on the outside, the smooth muscle cells. We placed the uroepithelial cells on the inside. We made this construct, placed in a bioreactor, and then placed that right back into the patient. And you can see here in the second panel the tubularized scaffold. On the far right, you see the tubularized scaffold with the cells already on them. And then here are the X-rays on the left of the injury. In the middle panel, you see the engineered construct being implanted surgically. In the third panel, you see the actual X-ray showing you the patency of the organ, and we published that series in The Lancet. Now, when we published that series, we had over a 5-year follow-up in these patients, actually up to a 6-year follow-up at that point, but up to a 5-year average follow-up, and you can see the pilot patients in this series. All the patients had a similar kind of injury. All the patients were treated the same way, and you can see the X-ray panels with the first panel showing you the actual injury, the second panel showing you the X-rays 3 months after surgery, and the final set of images showing you the injuries fully healed up to 6 years after surgery with the regenerated tissue. More important, though, is the functionality. What happened to these organs? And in fact, these organs continue to do well over time without any obstruction. We've been basically then, in this specific organ, we now have a long history of going after these tissues over 18-year follow-up, using these technologies with scaffolds alone without the cells, and we have used this strategy for many other tissues. We can use just scaffolds alone for limited distances. And then we now have over a 9-year follow-up using these scaffolds with cells for the more complex technologies on these patients. Same strategy for blood vessels. As you know, this has been a major area of interest by many, many investigators, and same strategy here. We basically take endothelial cells, we place those on the inside, smooth muscle cells on the outside. We then, for vascular structures, we've used bioreactors. We started using bioreactors about 18 years ago to really try to replicate the functionality of these organs as you're preparing them for implantation, really mimicking the functionality, the structure before you implant them. And this is actually carotid artery. That's the artery that goes from the neck to the brain that was replaced experimentally using these techniques. And this was highlighted in this journal, Nature Medicine. Of course, many investigators now that have carried work in clinical trials using various technologies for blood vessels, and this is an exciting area that is currently being pursued. Another structure we have focused on are heart valves. Same strategy here. We use bioreactors to condition these heart valves so they can start pumping away the way they should, basically conditioning them before they get implanted. And what happens with these heart valves is that you can see the actual conditioning occurring. You can see the heart valve leaflets opening and closing here. And this really leads to a very nice vascular endothelialization of this structure, so that the cells are attached to these structures and mature, so they don't slough off at the time of implantation. Now, this has not been done clinically yet at this point. This is still in the preclinical stage. We've talked about flat structures, such as skin. We've talked about tubular structures, such as blood vessels and urethras. Flat structures are the least complex. They're all complex. All organs are complex, but flat structures are by far the least complex. Tubular structures are the second level of complexity, more cell types, tubular in origin, not as complex as hollow non-tubular organs, which are really the third level of complexity. These hollow non-tubular organs are more complex because the cells are functionally more complex. There's more interaction with other organs. The architecture is more complex. But I'm going to use this organ to walk you through some of the strategies that we have used to engineer these organs and lead them all the way from the bench to the bedside. The number one thing that really needs to be done is to make sure that the cell biology is really well understood. The cells that are grown for these tissues have to be reproducibly the same time and time again, because that's your starting material. So a lot of work goes into the cell biology of cells. Same challenge here. We could not get these cells to grow. There was this natural senescence concept again, where people thought these cells could not be expanded. So by looking at the cell biology and looking after the committed progenitor cells, we could get these cells, harvest them, and expand them, and do so reliably where they retain their phenotype. Once we have the cell population, we then look at a family of over 30 different biomaterials that we mix and match to recreate the architectural structure of the tissue we're trying to replace. Basically, the scaffolds are going to be very different in terms of their properties, their biomechanical and structural properties, although they're all degradable over time. Once we have figured out the cell biology and the biomaterial sciences, we then start testing those cells with the biomaterials. We pick the right scaffold system, and we then start testing these in small animal models, such as rodent models, where we basically take the cells, we place the human cells on these scaffolds and place these scaffolds in athymic mice to avoid rejection. Once that occurs and we know that we're able to form the layering in these rodent models, and these models are used just for showing the layering of these structures, because the replacement is going to be okay no matter what you use in a rodent model. So we then go to a rabbit model where the size will make a difference. We then take and use scaffold systems and do a partial replacement to make sure that partially we can replace these structures in a rabbit model. And we then go to a total replacement where we go to the rabbit. Now we're going to do in the rabbit what we would do in a human. Basically, we take a small piece of the tissue, we grow and expand the cells, we then create the construct for the whole organ, we then seat the construct, go back to the same animal, and we then replace the entire organ with the scaffold and the cells that we implant. We use these bioreactor systems that are fairly sophisticated, that allows us to control the maturation of these structures before they get implanted. We then implant these, and it shows the x-rays of what happens to these structures over time. If we don't use the cells, if we use the scaffold alone, this is much larger than 0.5 centimeter from any edge, so obviously you're going to see scar tissue. However, if you do use cells over time, you see the natural progression of the organ radiographically. More important, however, is grossly. What do you see when you open up these structures? And you can see here that over time, these structures are maturing on the top panel. If you don't use the cells, again, they're going to stricture down because it's much larger than 0.5 centimeter from any edge. When we look at the histological characteristics and immunohistochemical characteristics, you can see the collagen, epithelial, and muscle phenotype that approximates that of the normal organ by 6 months. When we look at the molecular analysis, you can see the biology and regulatory and functional proteins that again approximate the normal organ by 6 months. When you look at the collagen deposition, looking at collagen 1, 2, 3, and elastin, we again see the adequate architecture of these structures by 6 months. When we look at the tensile stress, strain, the ability of these organs to be elastic and collapse, they again approximate the normal organ by 6 months. And this also we look at innervation. When we look at innervation, it again approximates the normal organ by 6 months. Innervation is extremely important, just as important as vascularization. So we actually take these tissues from the in vivo structures, and we then place those in vitro in organ bath studies, and we probe them to make sure that in fact they are adequately innervated, and the innervation approximates that of the normal organ by 6 months. And we then, this last our human experience. These are patients who were born with a Meyer-Rokitansky syndrome. This is a syndrome where there's a congenital absence of the organ. But these patients do have a rudimentary structure, so we can go in, take a small biopsy of the rudimentary structure, and then get these cells to grow. So what we did here is we took the biopsy from the rudimentary structure, we grew and expanded the cells, and we then seeded the cells on SIS, which is a Cook product, and we then basically seeded the cells on these scaffolds, so this is commercially available scaffold systems, and we then able to implant these structures right back into the patient. So basically what you see here is the rectum on the right, the bladder on the left, and the paucity of the organ, and then you can see here on the MRI, after the organ has been implanted, you see the rectum on the right, the bladder on the left, and now you see the new organ that has been implanted. When we look at these histologically, you can see that they do have the normal histology that is basically that of a normal organ, and we basically follow these patients up to 8 years after surgery to make sure that these organs continue to function well over time. And so basically up to 8 years, you saw the normal functionality of these patients, and that's when we published the paper this year in the Lancet. We really do follow these patients long term. We like doing a series of patients. We like treating the patients with the same conditions. We'd like to follow these long term to make sure that technology really is doing what the animal model did and is able to replicate it long term. The actual first structure that we implanted in humans as an organ was in fact the bladder. And this was a hollow non-tubular organ, so the level of complexity was very high. But same strategy here. If we had known then what we know now, we probably wouldn't have started with this level of complexity. But this really, starting with this organ, allowed us to go back to the less complex organs and go after them in an easier manner. But same strategy here. We basically take a small piece of the bladder tissue. We then, that's less than half the size of a postage stamp. We then expand the cells. The organ's made up of 2 different cell types. So these 2 different cell types are then expanded outside the body. 30 days later, we have enough cells for our construct. We start seeding the construct with the muscle cells on the outside, the urothelial cells on the inside. We then place these structures back into the in a bioreactor. We allow these bioreactors to mature the tissue, and then we're able to implant these back into the patient. You can see here the paper that we published for our preclinical series back in 1998. This is what led us to our human experience. In our human experience, we basically targeted patients who had end-stage failure, and they had failed all medical therapy. They were candidates for surgical reconstruction. We brought the patients in, did a 3D CT scan to configure what the bladder shape should look like. And this was really the precursor of what we started doing. We started bioprinting, basically doing the X-rays and doing a CAT configuration with software where we can actually use this to create these structures. We would then form the scaffold alone that would basically fit within the patient, and we would then coat that with cells. We would then place the cells on the structure, and you can see here the scaffold without the cells in an AP and lateral view. On the top, on the bottom left panel, you see the engineered organ being implanted surgically, and we cover that with a mentum, as you see here on the right. What you see here preoperatively is an X-ray of one of these patients with an end-stage organ, and then you can see the new organ after reconstruction. But more important was how these patients did with their bladder pressures. That's really why we did these patients. They had high bladder pressures, so it's important for us to be sure that we could keep these pressures low. If the pressures are too high, they get transmitted up to the kidney, where these patients can develop kidney damage. So basically on the top panel, you see the abnormal pressures, and in the bottom panel, you see the normal pressures after the organ was implanted. This is a paper that was presented by Dr. Alan Reddick, who was Surgeon-in-Chief at Children's Hospital, Harvard Medical School, showing what happened to these organs over time. showing that these were implanted in children. And basically, as the children grew, the organs grew with the children. So the organs were recognized by the body as being a native organ that grew as the patients ended up getting older. This then led to a second phase clinical trial, and basically early on what they showed was a lot of the patients were not cycled, and it's extremely important to cycle these organs, that is to allow these organs to fill and empty. If you defunctionalize them after you implant the structure, then you're not going to give that structure the cues that you need. And in fact, we're now leading to phase 3 clinical trials at our institution through a grant through the Armed Forces Institute for Regenerative Medicine using these strategies. But we published our initial paper back in 2006, and when we published that paper, we had up to an 8-year follow-up on these patients as well. Now, we've talked about flat structures such as skin, tubular structures such as blood vessels, hollow non-tubular organs, and basically the most complex organs are level 4 organs, which are the solid organs, because there's so many cells per centimeter that you just cannot have sufficient vascularity unless you have the right systems in place to engineer these. So one of the first organs that we targeted was actually the phallus. As Bernie mentioned, I am a urologic surgeon, and my area of specialty is actually pediatric urologic surgery. And there are many conditions where babies are born, just like the vaginal organs, with a congenital absence of the phallus. So this is an important organ as well. So the concept here was to take these cells. It's a very vascular organ, one of the most vascular organs in the body. The strategy here was to take a small biopsy of the organ, same strategy, grow and expand the cells. And this is really where we got stuck, because for the solid organ, even though we could grow the cells and implant them into scaffolds, we could get the cells to show histologically that they were normal, but we could not get the three-dimensional architecture that we required for these solid organs. And that's really when we started to think about how to actually create these solid structures. And this is what gave us the idea of actually starting to decellularize solid organs. So this is where we took solid organs, donor organs, that we brought into the lab, and we then started using very mild detergents to take the cells away from these solid structures. And then once we had this three-dimensional scaffold, we could then repopulate it with the cells in a three-dimensional architecture that would replicate that of the normal organ. We were then able to implant these back into the rabbit models, and we then went through the same process here: cell biology, material science, rodent models, partial replacement, until we ended up with a full replacement, which is what you see here. And when we did the full replacement, this is carbonosography that shows you the vascularity of the organ. On the left, you see the normal organ. On the right, you see the engineered organ, showing you that both have adequate vascularity. Of course, the controls did not do well. When we looked at the pressures, by 6 months, the pressures approximated that of the normal organ, and these pressures were sufficient for erection, copulation, ejaculation, and we were then able to mate these animals with their female partners. We were able to obtain sperm from the vaginal vault of the female partners, and this led to offspring, showing that these were in fact functional organs. And we published that in the Proceedings of the National Academy of Sciences back in 2010, where we are with this technology. We're moving forward into clinical trials for the next few years, again through funding through the Armed Forces Institute for Regenerative Medicine. This concept of decellularizing solid organs we kept pursuing with other solid organs as well. Back in the 1990s, when we started doing this decellularized structures, we started doing back in 1994, so 20 years ago. Shortly thereafter, we started doing this with other organs as well, like the liver that you see here. Same strategy. We started doing this back around 1997. We started using very mild detergents on the liver. We basically took a donor liver. 2 weeks later, we're left with something that looked like the liver. It felt like a liver. You could hold it like a liver, but it had no cells. But then you were able to preserve that vascular tree. And what you see here is a ferret liver that has been decellularized, and we're going to be injecting contrast through this ferret structure to show you how the vascular tree has been preserved, even though this has been decellularized and has no cells. We then were able to basically perfuse the vascular tree with endothelial cells, infiltrate the parenchyma with liver cells, and come up with these miniature liver structures that were able to secrete urea, secrete albumin, and metabolize drugs, as you see here. Basically, we follow the same strategy with other organs such as the kidney. Same strategy here. We take these organs, we decellularize them, reseed them, and have reconstitution of the cellular elements. But there's still a lot of work that needs to be done with these decellularized structures because of the clotting that can occur with these structures long term. So we can do this short term, but not yet long term, and that's some of the challenges that we still have with that strategy, and we're working towards that. Basically, that's really when we started thinking about bioprinting. And really the reason why we started thinking about bioprinting about 11 years ago was because we needed a strategy to scale up these structures and also get better vascularity that we were hoping to get with bioprinting. So this is a 2-chamber heart. This is using a very primitive desktop inkjet printer. Again, this is many years ago. We just took an inkjet printer. Instead of using ink, we used cells with a hydrogel. We modified these printers with a 3D elevator. So each time the printhead would go through, the 3D elevator would go down, and you would build the structure one layer at a time. You would build a structure 2-dimensionally to build a 3-dimensional structure, basically. Now you're going to see this 2-chamber heart popping out. And this was work done by Tao Zhu, who was a fellow at our institute. And basically you see here in the next slide, next slide, thank you. Thanks. This is, you see the structure beating, as you see here. The structure starts beating about after you take it out from the printer, about 4 hours later. It takes about 40 minutes to print. 4 hours later, the structure starts beating. And if you look at it under the microscope, then you see the cardiomyocytes beating together. And basically, at first you see the cardiomyocytes beating erratically, and then they start beating together. Again, this is very early work from many years ago, but this is really the work that led us to build the more sophisticated printers that we have today. And this is, again, where we started combining some of the technology we had developed with the earlier organs with the software. We would take these x-rays, and now some of these x-rays, this software is commercially available. TerraRecon, for example, is a company that has software that's commercially available that you can get in every major hospital. You do an x-ray, and then 3-dimensionally you can configure what the organs look like. So this is available anywhere. Basically, you can then take this information from that specific organ, transfer that information to CAD software and to a printing system that then allows us to take that information and get that into a printing structure that allows you to replicate the structure you're trying to print. And this shows our much more sophisticated printers now, where we have this strategy where you can basically print these structures over time. The principle here is a scaffolding technique. So some of our earlier printers, the structures did not have the rigidity necessary to implant these structures in vivo. So basically, we designed these printers so they would print a hydrogel scaffold and the cells with the hydrogel together, with the hydrogel having more firmness than the others. So you have this scaffolding technique that allows you then to create this structure layer over layer, but still retain the rigidity necessary for those structures long term. And here on the far right, you see these cells, and you may think, well, these cells look random, but not really. What you're seeing here is that these cells actually do have an organizational structure. On the top, you see these round shaped forms that we're printing over and over again. So in addition to scalability, these printers are giving you reproducibility. You're basically able to reproduce these. And then you can actually see the cell viability of these structures, and you can see how fine we can print. This is actually printing in color a liver structure with different cell types to show you how precise you can be with your printing. And now the latest technology we have is where we're actually using scanning and printing together. So the concept here is that if we bring a patient with an injury, a surface injury, we can actually scan the patient, look at the injury, and then go back and print over the patient at the same time with the right layering. This is basically a video depicting this in a cartoon, showing you how here comes the scanner first, and then you come with a printer printing the cells where they're needed. And basically this is something we're developing currently as well. Now, and this is actually a kidney structure that we have developed using similar strategies. We're able to grow and expand these cells in large quantities. We're able to seed them onto these three-dimensional scaffolds, and we're able to create these three-dimensional kidney units that we're able to implant into cows and steer. These are miniature, about the size of a lemon, and you're able to see the excretion of urine if you put them back into the same animal. Again, with a lot of these organs, you see the full organization of the cell structures. You can see here the glomeruli, the proximal tubules, the loop of Henle, the distal tubules. So the three-dimensional architecture of these structures gets preserved. If we implant them in a non-autologous organ, like you see on the far left, they're going to reject. But if you implant them in an autologous manner, they will survive and form normal tissue. When we look at the renal functional elements, looking at erythropoietin and vitamin D3, they approximated that of a normal organ. And we looked at the renal tissues in terms of their molecular markers and genes, they again approximated the normal organ. And this was highlighted in this journal. And basically, we've talked about the creation of organs. What about cell therapy? And you know, a lot of the meeting that we're going to see over the next couple of days is going to be on cell therapy. And basically, in terms of cell therapy, I think the same principles apply. You really need to make sure that these cells are well vascularized once you put them inside the body. So this is one of the technologies we have been working on for many years. Basically, same challenge here. You could not get the cells to grow. But we are now at the stage where we can go to a 75-year-old patient with end-stage renal disease, do a needle biopsy, and get enough cells to basically expand and repopulate that kidney. So the strategy here is you basically are able to retrieve these cells. This is a rodent model. On the left side, you see the area where the cells have been injected with a hydrogel. You see the area in the center. You see two glomeruli on the left that are marked there. And then on the right, could we go back one slide, please? And on the right, you see all the new glomeruli or nephron units that were formed after injection in that very same space. So basically showing you the formation of new kidney tissue using the right elements and the right vascularity, showing reversal of kidney damage in these rodent models. This is now in clinical trials in Sweden. This technology was licensed, and now they have been approved to do clinical trials here in the US. We also have looked at stem cell therapy in detail. And basically, as you know, there are three major stem cell types that are most commonly used experimentally and have been targeted for clinical use. And these include human embryonic stem cells and iPS cells, which are really great cells. They can go into any cell type possible. They go into all three germ layers, that you can grow them rapidly. But unfortunately, as you know, we have to be cautious when we do these in patients, because the cells by definition do form teratomas. They do form tumors, and they also have the potential to reject in certain instances. So, and that is why the first applications of these cells have been in very, very small organs like the retina, where you know the cell number that you can use is very low. A lot of the literature shows that if you inject these cells in volumes larger than 200,000 cells, that can lead to a higher chance of teratomas. The other cell type that has been targeted has been, of course, mesenchymal cells from bone marrow and other sources like cord blood. And again, these cells are very good cells. They can be used clinically. They can be implanted in an autologous manner, thus avoiding rejection. They don't form the tumors. But unfortunately, you can't really expand those cells in large quantities from the hematopoietic viewpoint. You can expand the mesenchymal stem cells, but you cannot expand cells that go into an ectoderm or endoderm phenotype readily. So on the one hand, we have cells that expand rapidly, but may form tumors and may reject. On the other hand, we have cells that will not form tumors, will not reject, but you cannot expand readily into two major germ cell types. So approximately 14 years ago, we started looking at an alternate source of stem cells. And we started looking at both the amniotic fluid and the placenta. It had been known in the literature for many, many decades that these are the cells that are coming right off the fetus, right off the embryo. So we basically asked a very simple question. From the cell population, could we get a stem cell? And interestingly, after many, many tries from both the amniotic fluid, which surrounds the developing baby, and the placenta, which is the afterbirth, it was really a fishing expedition with many markers. We were, in fact, able to locate a stem cell population that is c-KIT positive, that you're able to isolate and expand in large quantities from both sources, the amniotic fluid and the placenta. We were able to obtain these from over 400 pregnancies, and we were able to show these cells could go into all 3 germ layers, and you could use these cells either as a analog of human embryonic or iPS cells, where you could differentiate the cells to different cell phenotypes, or you could also use the cells in an immunomodulatory manner like adult bone marrow or cord blood stem cells. So basically these cells are very interesting cells. You can obtain them from both tissue sources, either before or after birth. They're neither embryonic nor adult, but have properties of both. They don't form the tumors. That is the major difference. Unlike HES and iPS cells, they don't form the tumors, but they can be rapidly expanded. They can double every 48 to 72 hours, just like HES and iPS cells. And unlike adult stem cells, you can expand them readily, and they do go into all 3 germ layers. There are 2 ways to use these cells. You can either store them for self-use, or a bank of approximately 100,000 unique specimens could supply over 90% of the U.S. population with a perfect genetic match for transplantation. Now, no cell is perfect, and neither is this one. And the weakness with this cell is that you do have to work harder to drive this cell into a specific phenotype. Whereas with a human embryonic stem cell or an iPS cell, they can go into a liver phenotype within 7 days. These cells, it takes about 20 days to do so. You have to go through more steps to differentiate the cells. But this is the same characteristic that does not allow the cells to form the tumors. They're slightly more developed than HES and iPS cells. We did stemness analysis on these cells, and if you were to picture human embryonic stem cells being at one end of the spectrum as the most primitive stem cells, and iPS cells being very closely related, and adult bone marrow stem cells being at the other end of the spectrum, these cells are somewhere around here, very, very closely related to HES and iPS cells with all the markers of pluripotency, including SOX2, OCT4, etc., but without the ability of these cells to form the tumors. This work was highlighted in this journal, and this cell type is now entering clinical trials, getting ready to enter clinical trials in several areas. What I've tried to do for you today is really give you an overview of where we are in this field that we call regenerative medicine. Basically, as you know, we're all excited. All of us here are working in this field. What I've tried to do for you today is really give you kind of an organizational structure of how we have gone about it ourselves. We've talked about using biomaterials alone, and this can be done for areas of small distances. We can look at the use of cells and biomaterials together for larger gaps. We can basically create these structures using either decellularized organs or bioprinting or scaffold systems. And there's a specific complexity that we go through in these organs, with flat structures being the least complex, tubular organs having the second level of complexity, hollow non-tubular organs the third level of complexity, and solid organs the fourth level. Up to this point, we've been able to implant the first 3 types of organs. We have not yet, of course, in the field implanted a solid organ, but there are clinical trials with cell therapies now active that I think will be very positive in the future. Basically, one of the challenges that I have when I give an overview of this type is, boy, everything looks so easy. And this is really directed to the neophytes in the audience. If you see this and you say, boy, this is so easy, you just put cells in a scaffold and there comes the organ. And of course, as all of us who are more experienced here in the audience know, it couldn't be anything further from the truth. These are very complex technologies. And the goal here is to really do a 360 on these tissues and structures as you develop them, where you really do have to look at these at every single level, at the molecular biology, molecular genetics, physiology, pharmacology, et cetera, as you develop these tissues. And I hope that one thing that I've really tried to underscore today is this methodical path that you need to take with this multidisciplinary approach. And we are very fortunate at our institute to have a really terrific team of investigators all working together to bring these technologies from the bench to the bedside. And this multidisciplinary approach is what we have done with the Armed Forces Institute for Regenerative Medicine. This is a national effort of over 30 different universities, all working together to bring these technologies to our wounded warriors. And you will hear a lot about that through this meeting as well. We basically have a wonderful team of investigators all working together to bring these technologies forward. And another strategy we have followed is to use these technologies for drug discovery and toxicity testing. So this is a program that we have called the Excel program, called Body in a Chip, where we're actually bioprinting these miniature structures so we can bioprint these organoids and use them for drug testing and drug discovery and toxicity. As an example, here are liver structures that we're able to reconstitute. They're very, very small. They're smaller than a pinhead. They cannot be seen to the naked eye, about 200 microns each, but they have all the cell elements that a liver has, and they form the same type of embryologic layering up to mature tissue that you see in a normal liver, and when you give them drugs, they can metabolize drugs, and they also can lead to toxicity if you use the wrong agents. I always like to show this cartoon before I close my talk, and this is a cartoon that shows a runaway stage. On the top panel, you see the stagecoach driver going A, B, C, D, E, F. He finally stops the runaway stage. Those are usually the basic scientists, and on the bottom, those are usually the surgeons. I am a surgeon, but really, when it comes to doing these strategies, we follow method one. You know, anytime in the research arena, we really do follow method one. And again, to underscore the fact that all these technologies have to be done very slowly and methodically. And any time that we have put something into a patient, we've made absolutely sure that we do everything we can preclinically to ensure success at the clinic as much as possible. And when we do these clinical trials, to them in a series of patients, where we can actually do a series of patients and then do the same defect and follow these patients long term before we proceed to the next level of the trials. This is a historical highlight from the journal Science, and it shows in the bottom left an iron lung. And when the iron lung came out, how many people here remember when the iron lung came out? Many of you. Well, you just dated yourself. This was many decades ago, but basically when this came out, this was considered one of the biggest advances in medicine. And the only place you see this now is in a museum. And people look at this technology now and they say, boy, wasn't that primitive. On the top right, you see an engineered organ, an engineered bladder. And I can assure you that 60 years from now, people will look back at these technologies and say, boy, wasn't that primitive. And that's the point, isn't it? That's why we're here. We're here because our goal is really to keep advancing the field and make our own technologies obsolete. At this time, I'd like to acknowledge some of the funding sources which have made this work possible, and finally, to leave you with a very brief video clip of a patient who was treated 13 years ago with an engineered organ. This is from an interview that he gave 10 years ago.
I was really sick. I could barely get out of bed. I was missing school. It was just pretty much miserable. I couldn't, go out and play, basketball at recess without feeling like I was going to pass out when I got back inside. I felt so sick. I was facing basically a lifetime of dialysis, and I don't even like to think about what my life would be like if I was on that. So after the surgery, life got a lot better for me. I was able to do more things. I was able to wrestle in high school. I became the captain of the team, and that was great. I was able to be, the normal kid with my friends, and because they use my own cells to, build this bladder, it's going to be with me. I got it for life, so I'm all set.
That's Lucas Masella. He's now 13 years out from having his engineered organ. We still have so many challenges in the field. We really do. We have scale-up issues. We have cost issues. We have the right choice of patients, the right choice of technologies. We still have many challenges. But one thing is certain, and that is that these technologies do have the potential to make patients' lives better. And that's the promise of regenerative medicine, to make our patients better. Thank you for having me today.
Excellent. Thank you. Great work. Okay. Yes. So this is where we break into our concurrent sessions, and I'm going to introduce in the discovery track in a moment Dr. Doris Taylor. Also going on at this same time, so you'll want to move to another room if you want to. We have at the RegMed Capital Conference, RegMed and Cell Therapy, the multi-billion-dollar industries with unlimited potential. Global regulation of stem cell therapies on the clinical and translation track. Hot topics, missing link for successful trials, the non-human primate imperative. And of course, Dr. Taylor here. I wanted to also remind all of the attendees, in your conference bag is the World Stem Cell Report in 2014. This was put together with my co-editor-in-chief, Graham Parker, as part of the wonderful journal Stem Cells and Development of Marianne Liebert. I also want to note in your conference bag, it might be a slightly heavy lift, but I encourage you to keep this book. You can put it in your room later. You don't have to carry it around all the time. It is a phenomenal book, The Inevitable Collision by Tori Williams, who's one of our featured speakers. Make sure you read this book. It's an incredible tale of patient advocacy. Dr. Taylor, if you would join me on the stage, please. So those of you with experience in the field, of course, have heard of Dr. Doris Taylor, who is with us today from the Texas Heart Institute. Dr. Taylor is a Texas all-star. She is the Director of Regenerative Medicine Research at the Texas Heart Institute. She's a pioneer in cell therapy and organ engineering. We look forward to her talk. Thank you.
Hello, can you hear me now? Yes. So nobody should have to talk after Tony Atala, and especially nobody should have to talk after Tony Atala when he's talking about building vaginas and building phalluses and already being in patients. I mean, really. I didn't know what Bernie was asking me to do when I said yes. So here I am, and this is going to be a lot more boring than that, I think, but at the same time, hopefully I'll get you excited about what we're doing at the Texas Heart Institute. I decided to talk a little bit differently today than I normally do. Normally I end up talking about organ engineering, but I wanted to really capitalize on what I heard Tony say and what the reality is, which is the biggest hurdle I believe we all face right now is not how to build an organ, but where to get the cells and how to get the cells to do that. And I want to talk a little bit about what I think is really one of the rate-limiting steps. But before I do that, I have to say welcome to Texas and remind you that I'm now at the Texas Heart Institute in the Texas Medical Center. And I saw several of my colleagues from Houston and the Texas Medical Center today, but to remind you, we're situated in the largest medical center in the world. 7.2 million patient visits a year. It's huge. If you can imagine it, we can do it at the Texas Medical Center. So I want to spend a few minutes talking about what I think we're actually trying to do here, which is not just trying to develop new therapies, but also, at least from my perspective, it's about defining injuries, defining disease, and contrasting and comparing that with health so that we can actually understand what goes wrong as we try to develop new therapies. And I'm going to use a couple of illustrations, including cell therapy, to really make the points that I want to make. And just to remind you that we've got a long way to go here, this is actually a diagram from a document called Mind to Market that was created in 1997 and really shows the capital stages of biotechnology commercialization, from imagining the idea of basic research through incubating it, demonstrating it, promoting it, and sustaining it. And you just heard Tony talking about the fact that he was doing some of this in the early 90s. We were doing some of this in the early 90s. And yet here we are decades later, and we don't yet have approved products. And I think it's important to realize that biotechnology cannot move forward faster than the technologies that support it. We can't get there if we don't have ways to grow cells. We can't get there if we don't have ways to make biomaterials. We can't get there if we don't have access to human tissues and organs. And we really need to recognize that and come together and try to create a viable model. Let's try the clicker again. Next slide, please. Next slide. So let's look back 6 months at where we were with cell therapy clinical trials in the cardiovascular arena. When you go to clinicaltrials.gov, in June of this year, there were over 500 clinical studies registered using the term stem cells in heart. Over 500. And about 200 of those are recruiting patients, which means that there are 300 studies that are either completed or no longer recruiting. And the vast majority of those studies are with autologous cells. Autologous cells that are being used for either treatment of peripheral vascular disease or coronary artery disease, ischemic heart disease, including acute myocardial infarction, some refractory ischemia studies, some post-infarction heart failure studies, and even end-stage heart failure. But given the fact that these are autologous cell therapy trials, it's important, the most important point I'm going to make today is that no two individuals in those trials are receiving the same drug. And if you think about it, if you look at some of the studies I've been most involved in, for example, through the Cardiovascular Cell Therapy Network, but even all of the bone marrow mononuclear cell therapy trials combined in a meta-analysis, 2,037 patients from 30 randomized controlled trials from 2002 to 2013. Bone marrow mononuclear cells used in 22 of the studies. And the bottom line was very little, 3 to 5% improvement in ejection fraction. No home run. Improvement, but no home run. And again, this meta-analysis said after 2 U.S. National Heart Lung Blood Institute trials of roughly 100 patients each came back negative, and I was involved in those trials, there will likely be a shift in the focus in domestic stem cell research, a lot of interest in America and moving away from bone marrow mononuclear cells and moving forward with alternative cell populations. And those trials that are now being focused on are Scipio, Poseidon, and Caduceus. And I'll talk about those. But before I do that, I want to ask the question, why is there variability in these earlier bone marrow mononuclear cell studies, and what can we do about it? As I said, if you're giving autologous cells and they're derived from your own bone marrow, if I took bone marrow from you, and I looked at that bone marrow, it would be different. Nobody has exactly the same composition of bone marrow. That's not surprising. If we all had the same composition of bone marrow transplant would be easy. It's not. We all know that. That being said, we don't know what the right cell is. We don't know what the right dose is. We don't know what the right time is. And when you're doing autologous cell therapy and you're giving every individual a different drug, it's like giving a different drug, not even knowing if you're giving the drug in every patient, really not being sure how much you gave, and then getting to the end of the study and saying, we're looking for a signal. And we're looking for a signal in the treated versus untreated. The fact that there's any improvement at all, I think speaks to the potential potency of these therapies if we actually understand them and do them right. So why is there variability? Well, one reason is that at best case, there's 25% retention of cells. The vast majority of cells we give into the peripheral blood, into the heart, disappear over the first 48 hours. 25% are left. Moreover, every cell type that's given has multiple mechanisms of action, and we don't really understand what those are. They can be everything from wound remodeling to neoangiogenesis, to immune modulation, to differentiation, or even some sort of paracrine signaling. We don't exactly know how cells are behaving. I told you only 25% get retained. We don't know which 25%. We don't know which cells are there and which ones aren't. So we're really working in a black box. So we did something a few years ago to try to answer that question. In 2006, we said, duh, everybody's getting autologous cells. Let's take the excess cell product and measure it. Let's profile it. So we actually formed a biorepository and cell profiling lab for the NHLBI, where we received bone marrow mononuclear cells from patients who were enrolled in these trials, and we actually measured immunophenotypes, 40 different cell surface markers and cell populations, cell function, and colony-forming assays, and different indicators of cell potency or signaling, and we stored products to be able to do DNA and RNA analyses, which we're now doing. So we could store the products for up to 10 years, characterize their product, and that would allow us to generate hypotheses about what's happening. Why would we want to do that? This is a slide that came from Carrie Kimler at the Texas Heart Institute. Why would we want to do it? Because really having clinical samples tied to patient data and tied to patient outcomes in clinical trials is invaluable. And it's not just about genomics, it's about so much more than that. Genomics is the potential in my mind of cells, but the reality is what cells are there and how they function. So why would we want to do that? Because ultimately we want to be able to use these cells and patient outcomes to begin to look for new drug targets, to investigate how cardiovascular disease happens and biomarkers associated with progression of disease, to screen patients who may do well and may not do well. Imagine if we can find biomarkers associated with the ability to respond. Then not only can we say this will decrease the number of individuals you will potentially need in your trial because we can help you enroll patients who will respond, but moreover, we can tell you who it's unethical to enroll because you know they can't respond. And we can also begin to provide personalized treatments based on disease characteristics. And moreover, we can actually take the data that we generate and go backwards and actually begin to use these to do a more broad-based community-type screening and understand and actually recruit patients to our hospitals, our medical centers, because we have treatments that are valuable for them. One of the things that's turned out to be interesting is we've not only done this now for cell therapy, but we've also done it for gene therapy. And what's really becoming fascinating and fun is we can predict, if you think about it, how's a gene therapy going to work? It's got to work at the level of a cell, right? Genes don't do anything if there are no cells. So what we've actually been able to show is that there are certain cell populations that change in response to a gene therapy as well. That being said, over the last few years, what really drove this for me too was my belief, and I see Aubrey here, my belief that I've posited for a number of years now that aging and diseases associated with aging are really a failure of stem cells. That our ability that endogenous repair is the norm. If you think about it when you're a child, if your kid gets a cold, if your grandkid gets a cold, it lasts 2 days. I get a cold, it kicks me for a week. So let's just say that endogenous repair is the norm, and when we're young, we have the cells present to repair our organs and tissues all day, every day, unless there's a catastrophic event or some sort of genetic intervention. We have stem cells in virtually every organ or tissue or in bone marrow. Moreover, when we have an injury and an inflammatory signal occurs, that's basically nature's cue to say, help, send me cells. And if you can get the appropriate cells there, you can turn off the inflammatory response and actually repair the injury. But if you don't, your body ramps up the inflammatory response saying, hey, I said send me cells. And then you actually start recruiting pro-inflammatory cells that cause secondary damage. So a number of years ago, we said, let's do cell therapy because we know these injuries like a heart attack are occurring in a catastrophic fashion over a time period where we don't have the time to ramp up the cells we need. So let's harvest those cells and deliver them to the appropriate target and show that we can actually mitigate the effects of the injury. But we want to prevent the flip side of that, which is uncontrolled cell proliferation. Nobody wants to be the person saying the good news is you no longer have an injury, the bad news is you now have a tumor. So let me go back one. But we also have found that stem cell numbers decrease as we age. And this is a very preliminary early graph showing a specific stem cell population in individuals from age 18 to age 75. And what you see is those cells decrease dramatically over time. Now what I'm not telling you is this is stem cells in men. We women, we rock. Ours don't go down to the same degree. Now, what you also probably know is that women don't develop heart disease as early as men. We don't catch up with men in terms of cardiovascular disease until about the 7th decade of life. And what we've found is that there's a threshold below which it seems that these cells fall, and then you begin to develop chronic diseases. I'll come back to that. So let's go back to the cardiovascular cell therapy trials and what we've learned based on our biobank, okay? This was the FOCUS study, FOCUS CCTRN study, which was the effect of transendocardial delivery, so direct injection via catheter of autologous bone marrow mononuclear cells on functional capacity, left ventricular function, and perfusion in chronic heart failure. So these were patients who had already had ischemic heart disease, greater than 30 days post-injury, and they had cells delivered. And what actually the outcome of the trial was negative. There was no difference in left ventricular insystolic volume, no difference in VO2 max, However, there was an improvement in left ventricular ejection fraction. Now, I want to make 2 points about this trial. One, if you're getting involved in the cell therapy field and you're going to do clinical studies, think carefully about your endpoints. Because normally, in every cardiovascular cell therapy trial, left ventricular ejection fraction would be your endpoint. We decided to get fancy and not use ejection fraction as a primary endpoint. And guess what? Ejection fraction was positive and all of our primary endpoints were negative. So the trial is negative. So be careful. That being said, we chose to then capitalize on the fact that even though the endpoints are negative, if you look at both the bone marrow treated BMC group and the placebo group, there are patients who did better. You see the decrease in end-systolic volume there in both groups in some patients, and you see some patients whose VO2 max got better, went up in both groups, and you see patients whose EF went up in both groups. So I said, let's take all the individuals who did better, and who did better in either 1, 2, or 3, all 3 endpoints, and compare them with the controls and see what we know about the underlying ability to respond in these trials. And what we found was very interesting. Now let me remind you, we gave bone marrow mononuclear cells to these patients. And when you go out in the world and you hear about a bone marrow mononuclear cell trial, you're hearing about a stem cell therapy for whatever it is, right? Cardiovascular disease, stroke, spinal cord injury, whatever it is. 95% of the cells you're giving are bone marrow cells. 1 to 3% of the cells you're giving are stem or progenitor cells. And yet, we're all assuming that we're doing stem cell therapy. And what we found was that, in fact, if we looked at our triple responders, the people who got better in all 3 endpoints versus those who did not, versus those who only got better in 1 endpoint, 2 endpoints, or versus those who got worse, that in fact there were several cell populations that were increased or decreased in their marrow at the onset of the trial. And those cell populations were primarily what we call CD19, CXCR positive cells, aka AB cells, or CD1 positive cells that are probably monocytes, macrophages and monocytes. And a small number of CD34 and CD133 positive cells. But in fact, the vast majority of cells that were changed were not stem or progenitor cells. And in fact, what we found when we looked at functional, the only thing we'd say is when we looked at functional capacity, patients who had more potent endothelial cells did better. So what did we learn? Well, we were reminded that stem cells are only 1 to 3% of the cells, that the other 95 to 98% can't be ignored, that patients differ, that comorbidities matter. That is, patients who had diabetes or patients who were on statins. How many of you know people who take statins? Vast majority of you probably. How many of you knew that one of the pleiotropic effects of statins is they mobilize stem cells? So the reality is we can't ignore the underlying processes that are going on that probably play as much of a role in the response to treatment than as the treatment itself. And that if we can actually understand that, we can predict which patients should be enrolled in these trials. Interestingly, the two most important predictors were age and sex. And I already showed you the data here that stem cell numbers go down as we age. What I can also show you is that if you look at patients under the age of 60, and you look at VO2 max, you can see that those in the treatment group did better than those in the control group. So if your stem cells are younger, they're more potent. Unfortunately, our stem cells aren't younger unless we're younger. So what we've actually started, and if we actually went back and looked at these trials and looked at the relationship of age with endpoints, individuals who were under age 62 also had a better improvement in ejection fraction, much better improvement in ejection fraction, whereas individuals over the age of 62 did not. Now, that's not great news if you're over age 62 unless we can do something about that. So the real question in our mind became, are there good cells that are gone, or are there bad cells that have accumulated? And we think it's a combination of the two. Remember I told you inflammation, in my worldview, is basically nature's cue to say, send me cells? Well, over time, what we've also showed in a number of our patients is that inflammatory cells accumulate. So the future may be about reducing some of these negative cells as well as increasing the number of positive cells. So let me very quickly answer what we've learned and then go forward to something else that we're working on. So what have we learned? Well, as I said, we've learned that each patient receives a different drug, that stem cell numbers differ per patient, cell numbers decline with age, they decline with chronic disease, they're mobilized differently in each patient, so we can either repair the cells or choose better cells. One of these, I believe, are really the only options. Repairing the cells, we're actually working on that with gene modifications at Texas Heart Institute. I'm not going to focus on that today. You can select other more potent cells. You can find alternative cells to bone marrow cells. You can use allogeneic cells, or you can go home. One of the options, as I said, is to choose a different bone marrow-derived cell. So more recently, in collaboration with Aldegen, we actually began a clinical trial in the Cardiovascular Cell Therapy Network looking at an aldehyde-bright population of cells in heart failure. There was a preliminary study published in 2012 showing that you could take these cells characterized by their enzymatic activity as stem cells, so a very small population of bone marrow cells, and deliver them the same way we delivered others, decrease end-systolic volume, improve VO2 max, and improve perfusion. You can see some of those spec data here. We could also choose autologous sources. We could choose adipose-derived cells. The PRECISE trial was a randomized double-blind study of transendocardial delivery of fat-derived cells. The ultimate irony is that as we age, our fat cells don't decline in potency. So basically, you can get a liposuction and a cell therapy at the same time. And as an aside, plastic surgeons have known this for a long time and actually have been collecting these cells for years. But we found that in ischemic cardiomyopathy, these cells would actually reduce infarct size, as you can see here, and would improve VO2 max. That led to the Athena study, which is underway, which is a phase 2, 2-to-1 randomized double-blind trial in 45 patients at 6 US centers. And I also mentioned that the Scipio trial earlier. You can also go to other tissue sources. The Scipio trial is a cardiac stem cell trial underway using cardiac biopsy-derived cells. Scipio's already been published. It was a pilot study of 23 patients with a previous heart attack and bypass, and they had an EF of less than 40%, an ejection fraction of less than 40%. In those patients, intracoronary infusion of these autologous, self-derived cardiac stem cells was associated, it was safe and it was highly efficacious in terms of improving ejection fraction and decreasing infarct size. Caduceus, another cell therapy study with different population of cardiac progenitor cells, also highly efficacious, delivering the cells and decreasing infarct size, improving global function, changing heart failure class. And then finally, you can look at, you know, if I'm over 62, I'm not yet, but I will be, knock on wood, beats the heck out of the alternative, right? And I want cell therapy, then maybe I'll go to a young, healthy allogeneic donor. And in fact, companies have built their whole business model around going to Olympic athletes and deriving cells and storing those for use in patient populations. So one approach is actually deriving mesenchymal cells that can actually be derived from bone marrow or from fat, from a non-ischemic, from a young donor, and delivering those cells in 60 patients. And you can see in that trial, in-systolic volume declined over time, in diastolic volume declined over time, dilated hearts got better, and in fact, people lived longer. So that has led to a phase 3 TEVA cardiac pivotal trial, 1,700 patient clinical trial that's now been initiated in the US. Finally, the other option is screw all these, you know, choosing better cells. Let's just actually go back to the old standard bone marrow mononuclear cells and look at a different outcome. And in Europe now, the BAMI trial is underway. That is a 3,000 patient randomized controlled trial giving bone marrow mononuclear cells after a heart attack and looking at all-cause mortality as the outcome. And in fact, we anxiously anticipate the results of this trial. Okay, switching gears entirely now for the last little bit of my talk. You know, I believe that cell therapy is going to be beneficial. But I also believe that it's highly unlikely that we're going to take end-stage terminally failing organs and move them fully backwards with simply cells. And so we believe, like Tony and others, that the unmet need is for organs, not just for cells. And we've actually taken a different approach than Tony to try to generate organs. People die every year waiting for hearts, for lungs, for livers, for kidneys. Can we go forward, please? And yet you can see, oops, I'm sorry, you can see, there we go, perfect. You can see while the need for organs, number of individuals on the waiting list in the top graph keeps going up, the number of transplants has not increased significantly in the last few decades. And that's because we simply don't have the organs that we need. So we said, and I'm a scientist, but I'm also a believer in changing the world and doing whatever you can imagine. So we said, can we build an organ? Now, I'm not a tissue engineer. Unlike Tony, I don't think about biomaterials and cells and all of those things together. But what I do know is that our mantra in my lab, and I learned this doing cell therapy when my group was the first to transplant cells in the heart, and the New York Times called me and they said, if it's so easy, why hasn't somebody done it before? And I said, I don't know, I guess because nobody believed it could be done. So when we got ready to build an organ, we said, okay, how do you build an organ? We said, we don't know, but how hard can it be, right? So you really just need three things. And I will concur with Tony's point that if I had known then what I know now, I might have done it differently, but I'd like to think not. So what do you need? Well, you need cells. And I'll come back to this because I think this is actually the biggest hurdle in the field. But you also need a place to put those cells because cells alone do not make an organ. You've all seen pictures of beating heart cells in a dish, and if you haven't, I'm going to show you one. But that is not a heart. Just like the little liver vesicles that Tony showed us that he can build on a chip is not a liver. It's a piece of tissue that you can use in the lab, but it's not an organ. But more than cells, you need a place to put those cells to make them function. And we said there are really just a couple kinds of options. You can use a synthetic scaffold, you can use a biologic scaffold, you can use a mechanical scaffold, or you can do, like you heard Dr. Atala say, and bioprint a scaffold. But when you do that, you have to have a scaffold that can function. In the case of the heart, it has to be able to pump, has to be able to pump against a blood pressure, has to be able to survive long term. If you're going to build a liver or kidney, you have to be able to use it for metabolism and filtration. So it's also about physiology. Now, we took a simple approach, which is decellularization. And because we said we were used to hanging hearts in the lab to try to get an organ, get cells out of the heart, we said, let's hang a heart in the lab and see if we can get rid of the cells and keep what's left. Because I think nature has figured out how to build scaffolds pretty well. So on the left, you see a time-lapse video of a rat heart. Actually, can you click the movie again? To actually show the decellularization process going from a red muscularized organ, thank you very much, to a completely acellular scaffold. And then on the right, you can see a large cadaveric heart undergoing the same process. But you can do it for any tissue or organ. You can do it for heart, you can do it for liver and gallbladder, you can do it for kidney, and on the bottom right, you can see pancreas and actually gut. So no matter what, you can actually use the vasculature to decellularize these constructs. And what's so important about that is because you use the vasculature, when you're done, you have all the things that Tony said you needed. You have a vascular tree. You have a vascular tree that works. Look at this. This is just one image of a liver and a kidney after we decellularize them. And if you look on the top, you can see the vessels in the liver by electron microscopy. They're gorgeous. I didn't show, and on the bottom right, you can see actually a glomerulus in a decellularized kidney. With all due respect to everyone in the world who's bioprinting, I don't want to spend the next 20 years figuring out how to print that. Nature's already done it for us. So why can't we take advantage of what nature's done and use that? So what we said is, let's take human organs that are not suitable for transplant. Here's the first human heart that we decellularized. And you can see on the top left, the heart, first of all, it's covered in fat, no comment. Secondly, you can see that on the bottom right, where all the red muscularized region was on the top, is missing. That we just have a pale, clear, acellular organ there. And for the sake of time, I didn't go through all of the videos that I would normally show, but this is an OCT of the left anterior descending coronary artery. We basically put a camera inside the coronary artery, and you're looking down that coronary artery. And what you can see is the inside of that artery is intact. It's not broken down. The surface looks great. And you can see the branch where there's actually a branching of the artery, but the artery is intact. And we've done a number of studies showing that we can infuse blood into these. And in fact, the vascular tree is beautiful. Why decellularized matrices versus devices or bioprinting? Structure. Everything is there. The macro and microstructure. The composition. There are over 100 different proteins and sugars left in this matrix that we create. It's going to be very difficult, not just to recapitulate 100 proteins and sugars. You can do that, mix them all together in a 3D printer and print them. But doing that in the same spatial orientation, knowing exactly what's where, because it's not a homogeneous organ. If we take the right ventricle of the heart and the left ventricle of the heart, the proteins are very different. And you know what? If we take the same cells and we put them on the right ventricle and we put them on the left ventricle, they pump differently, they have different force, they differentiate differently. So those proteins matter. And in addition, the matrix is functional. Nature knows how to do it. So if we think we've got a scaffold, where are we? I would say that brings us back to cells. Is it possible to click on that video? And if not, nope. Okay. Then, there you go. This shows cardiac stem cells beating in a dish. And it shows you that we can create cells that pump, that beat. But like I said before, we can't create cells that beat with high fidelity. And if we're going to, what I didn't mention earlier is every time someone has a heart attack, they kill about 1 billion cells. 1 billion cells is about a cubic centimeter of tissue. Something like this. Okay? Our hearts are about the size of 1.5 fists. We need way more than 1 to 2 billion cells if we're going to generate a heart. In fact, we need hundreds of billions of cells. And if I want to build an autologous organ, we need those from an autologous source that can be grown reasonably quickly and give rise to the cells we need. So what are the hurdles to that? Hundreds of billions is difficult. It's even more difficult at an affordable cost. The growth media, we actually calculate that to grow 100 billion cardiac stem cells costs us on the order, just stem cells, not cardiomyocytes, costs us on the order of about $12,000 to $15,000. To grow 100 billion cardiomyocytes costs us on the order of about $40,000 or $50,000. And that's right now doing it under non-GMP or GLP conditions. So you can imagine. Moreover, we need cells that can give rise to all the complexity of the heart. Atria, ventricle, pacemakers, neurons, fibroblasts. We even need cells that can stay stem cells. Because if you think about it, if we're going to transplant any of these organs or tissues, they have to be able to repair themselves as well as the native organ or tissue going forward. And they have to be able to respond over the long term, and they have to live for years and years and years. If we're going to, Tony showed the video of a young man who had received a bladder 13 years ago. In regenerative medicine, unlike virtually any other therapy, we can't turn it off or take it back. Once we give it, it's there. So we need to know how to give it in a way that is safe and effective for the long term. So again, what are the possible cell sources? ES cells or iPS cells. The problem is, turning those into heart cells, we have about a 0.2% efficiency. Pretty abysmal at present. Cord blood cells or the amniotic fluid cells that Tony talked about, tissue-derived stem cells, blood, bone marrow, fat, and muscle, or revitalized bone marrow or fat stem cells. But again, we've taken a different approach, is can we let nature do this for us? I don't want to have to figure out how to grow all those cells. I either want to partner with somebody who's already doing it, or I want to let nature do it for me. So we took a couple of approaches and we said, can we just take a piece of matrix, and then this is a rat heart where the decellularized matrix is relatively thin, and you can see here that it's on the surface of an infarcted heart, and we said, can we transplant that a week after a heart attack and then look at the results in vivo? We've also done this in pig, and this is a video of actually one of these patches going into a pig heart. And what you can see histologically a month later is a couple of things. One, if you look at if you look on the right, you see there's vasculature. There are circles there that weren't there previously. And the patch is on top of those circles. The patch got revascularized. In addition, on the left, remember, we put the patch in with no cells in it. So on the left, we actually captured an image of cells migrating into the patch. The patch recruited host cells. And if you look at those cells, we labeled all the nuclei blue, and we labeled with different antibodies in red, and you can see CD45 on the upper left would be a marker of inflammation. Any white blood cell or neutrophil or macrophage would be CD45 positive, and very few of the cells are positive. Very few of the cells express a marker called VEGFR2, a marker of stem cells. Very few express c-KIT cells. You can't see that well in here because of the lighting, and a few express CD103. But if we look at a marker of cardiac stem cells, PDGFR2, you can see there are huge numbers of them present, and they're actually starting to differentiate. Moreover, if we can also potentially take these cardiac cells, put them on the matrix in a dish, and you can see a little piece of that matrix is beating there. We can let nature drive the organization of that. Here's our decellularized matrix, and here's our matrix plus those cardiomyocytes. It's gorgeous. I thought this was a histologic image of a normal heart when I first saw it. It stunned me. So the matrix is smart. It can tell the cells what to do. We can do that with vessels. I showed you intact vessels. We can recellularize a whole heart and the vasculature. Look here on the bottom left of endothelial cells, smooth muscle cells put into one of our hearts, and you can see the vessels fully relined with cells. It's gorgeous. Moreover, we can, because whole heart is the end game, I've got about 3 more slides, you can see that we can actually transplant these 100 billion cells into a whole heart, and we can actually try to give it a shot. And here's our bioreactor with our first 100 billion human cells in it. But what I learned very quickly is that all sorts of nature likes to grow when you're trying to grow an organ or tissue in a bioreactor, and it's very easy to get these infected. So we said, okay, let's go back to our first principles and let's actually try again to let nature do this. So what we did then is we took one of these acellular hearts and just transplanted it in an animal. And we said, let's see what happens. I can't seem to. So here's what we did. We took one of these hearts and we did a heterotopic transplant. We transplanted it next to the existing heart in a pig. We've done it in a pig and a cow now. We're doing another one this week. We've done 4 or 5 now. And then we said, let's just get out of the way, close the animal up, and wait 60 days and see what happens. 60 days later, this is what we had. It's pretty remarkable. We've actually dissected these. We've looked at the histology. There are muscle cells growing in. There's vasculature. There are revascularized cells. Now, do they pump yet? Well, no. However, what we know in our bioreactor is that none of these cells ever mature unless we give them a blood pressure to work against. So we have to give them load and a blood pressure. So now, and we have to train them to be synchronous. I showed you cells beating in a dish, but they don't all work together unless we train them. So now our next experiment is transplant one of these with the pacemaker attached, and as the cells migrate in, turn on the pacemaker and make it work for it. And we'll let you know what happens. Final slide. You're in Texas. I saw this in Austin this summer. It says, I wish I could trade my heart in for another liver. That way I could drink more and care less. Somebody was having a bad week. So we said, can we do this with liver? And can you possibly click on that image? Tony showed you a similar image. This is our view of transplanting cells into liver, and you can see in real time it takes all of about 30 seconds. These are primary human hepatocytes going in. Actually doesn't look like it's going to play, but you can see on the bottom that in fact we have a liver construct. There you go, here you go. That's it. That's literally the cells going in. And a month later on the bottom, we have the construct here, and you can see that the construct, primary human liver cells that Tony said you can't keep alive in a dish, we kept alive for 30 days metabolizing drugs just like they did at 2 hours. So we're pretty excited about that. So where are we? I'm going to close by saying I think we're exactly where we are with organs. We're in the same place we are with cell therapy, which is we've moved forward very rapidly, but now we've got to convince ourselves and the world that it's not just a one-off phenomenon and that we can figure out how to do it reproducibly and potently. I'm going to close with this slide. First they ignore you, then they laugh at you, then they fight you, then you win. It's a Mahatma Gandhi quote that I think you have to take with you if you're going to work in the field of regenerative medicine. And then I have to thank my colleagues and show you this final slide, which is one of our THI branded hearts, because now I work in Texas and we brand everything here, even our boots. And if you want to be in touch, just give me a call or email us. Happy to talk to you. Thank you very much.